The focus of this video is on understanding the normal curve and how deviations and the mean are plotted on the normal curve using something called z-scores. In addition, we'll review probability in particular as it relates to the normal curve, but also in situations beyond the normal curve. When statisticians are working with quantitative data, they often summarize those data using the mean and standard deviation. Keep in mind that the mean and standard deviation should only be used with quantitative data. Therefore, qualitative data will not be a focus of this video. A sample mean summarizes where scores tended to fall, whereas a standard deviation for a sample summarizes how far around the mean scores tended to fall. You may have heard of quantitative data referred to as normal before. This has a very specific meaning. When we say data are normal, several things are true. I'm going to focus on two of those things for now. First, when data are normal, it indicates that the mean, median, and mode are all either equal or very close to being equal. That means the mean, median, and mode are the same or very similar numbers. In addition to this, about 2/3 of scores are expected to be within one standard deviation of the mean when data are normal. Let's take a look at a scenario where we have quantitative scores with a mean value of 100 and a standard deviation of 15. Presume that the data, the raw data, are normal. Another way of saying this is presume that they are normally distributed. Calling data normal or normally distributed means essentially the same thing. If our data are normal and the mean is 100, then the median and the mode are also expected to be 100. Further, if the data are normal, we expect about 2/3 of the scores to be within one standard deviation from the mean. What this means is we expect about 2/3 of the scores to be at the mean plus a standard deviation to at the mean minus one standard deviation. So in this case, we expect about 2/3 of scores to be at 100, give or take 15 units. If we add 15 units, that gives us 115. If we subtract 15 units, that gives us 85. So in this scenario, if the data are normal, we expect about 2/3 of scores to be between 85 and 115. That's one standard deviation below the mean to one standard deviation above the mean. How about in this scenario? Let's say we have quantitative data which are normally distributed, where there is a mean of 50 and a standard deviation of 2.5. First, pause here and decide what the approximate median and mode would be, then hit play. You should get that the approximate median and mode are 50, because when data are normal, the mean, the median, and the mode are all the same or approximately the same number. Now consider what the range of scores is where we expect 2/3 of the raw scores to be. Pause and hit play when you're ready. What you should get is that the range where we expect about 2/3 of raw scores to be is from 47.5 to 52.5. That's from one standard deviation below the mean to one standard deviation above the mean. Let's review this concept using a histogram. A histogram looks kind of like a bar graph, where a quantitative score or variable is placed along the x-axis from lower scores on the left to higher scores on the right. And then on the y-axis, we have the frequency with which those scores occurred, from lower frequencies on the bottom to higher frequencies on the top. Suppose I measured depression using a 14-point quantitative scale. The scores for depression would appear on the x-axis, and the frequency with which each of those scores was observed would appear corresponding to the y-axis. Now let's say that I plot out my data, and I see that the mean score was a 5. I also notice that that's the modal bar because it's the tallest bar in a graph, so the mode is also 5. And if I were to look at this symmetrical descent of the two sides, I would see there's an equal number of cases to the left of the center bar as to the right of the center bar. So the center bar of 5 is the mean, the median, and the mode in this graph. These data are approximately normally distributed because we see a couple of key characteristics of the normal curve here. First, as was just noted, the mean, median, and mode appear to be the same number. Another thing we look for is symmetry. That is, if we slice the graph down the center, do we get the same picture on the left side of the line as on the right side of the line? If we were to fold our graph in half along that central line, would it look the same on each side? And this is approximately true in our drawing here. So not only do we have the mean, median, and mode at the center, but if we were to create a crease on our graph there, we see that what's going on the left side of the graph and what's going on the right side of the graph look the same. Another feature of the normal curve is that the tails, or end sides of the graph, are asymptotic. What that means is they seem to be approaching the axis, in this case the x-axis, but they're not necessarily descending to hit it theoretically. Now, whenever we have real data, our graph will end at some point along the x-axis, but theoretically, if we continue to collect data, we would expect to see these bars get smaller and smaller as we continued along the x-axis, without necessarily ceasing at any certain point. So visually, there's a few things that we see here that are indicators of normality. First, the mean, median, and mode appear to be equal. The two sides of the graph appear to be symmetrical, or even. And the tails, or ends of the graph, are appearing to be asymptotic. Again, what this means is that the graph is getting closer and closer to the x-axis without necessarily hitting a 0 point on the x-axis or descending below the x-axis. When data are normal in your histogram, you can do what's kind of like a connect the dots of the bars to create what's called a frequency polygon. A frequency polygon is a shape indicating how frequently different scores occur rather than the bar version of the graph. Notice that when I color in the polygon, I get this kind of bell shape. And then if I remove those black lines, the bell shape becomes even clearer. This is why the normal curve is often also called the bell curve or the bell-shaped curve. The same thing is being indicated here as in the histogram version, that as we get closer to the center of the graph, scores become more common, and as we move away from the center, the sloping nature of the graph indicates that scores are becoming less common. Now suppose here that our mean was 5 and our standard deviation was 2. Well, we would expect about 2/3 of the scores to be between 5 minus 2 and 5 plus 2. That means we would expect about 2/3 of the scores to be somewhere between a score of 3 and 7, here and here. So we expect about 1/3 of the scores to be from one standard deviation below the mean to the mean, and another about 1/3 of scores to be from one standard deviation above the mean to the mean. When you put these together, we expect about 2/3 of scores to be from one standard deviation below the mean to one standard deviation above the mean. And if you color in the graph and look at it visually, you can see that about 2/3 of the graph is colored in if I shade the region from one standard deviation below the mean to one standard deviation above the mean. This graph is approximately the same and true for any quantitative data set which is normally distributed, regardless of what the mean and standard deviation are. So I can change these means and standard deviations and plot them onto the exact same graph. For instance, let's assume I collected data on how many ounces of water individuals consumed, and I found a mean of 60 and a standard deviation of 10. I'd plot this the same way, going up and down one standard deviation, and then I can continue these movements along my axis. Here, the shape of my graph, assuming that the data are normal, does not change. And the segments of the graph, such as the area that's around the mean, or we expect 2/3 of folks to be, does not change. What does change instead is the numbers that we put on the x-axis that correspond to the graph, but the graph itself doesn't change. Now notice here I scooched the y-axis over a little bit to give us space, but I didn't change anything about the graph shape itself, just where it fell along the x-axis and which numbers went below it on the x-axis. The benefit of the graph is that it allows us to compare different quantitative variables when each of those variables are normally distributed. I can look at one graph for height and compare it to a graph for weight, and I expect the shape to be approximately the same if the data are normally distributed. To simplify this and use means and standard deviations to make comparisons, statisticians oftentimes compute something called a z-score. A z-score tells us how many standard deviations each raw score is away from its mean. Suppose I had a data set where the mean score was 60 and the standard deviation was 10. And suppose that even though I don't have all the raw data from the data set, that I know the raw scores for 3 persons in the data set. Person 1 has a raw score of 60, person 2 has a raw score of 70, and person 3 has a raw score of 55. Presume we would like to know how many standard deviations each of these people are away from their sample mean of 60. We can compute this by finding the z-score. The z-score is computed as raw score minus the mean score divided by the standard deviation. So let's take a look at person 1. Their z-score is equal to their raw score of 60 minus the sample mean, which was also 60, divided by the standard deviation, which was 10. So we get 0 over 10. This person's z-score, therefore, is 0. The z of person 1 is equal to 0. The reason is because this person's raw score is the same as the mean. When a raw score is equal to a mean, the z-score will be 0. This is because z-scores tell us how many standard deviations a score is from the mean. And if the score is exactly at the mean, it is 0 standard deviations away from the mean. Let's repeat it for person 2. To get their z-score, I need to take their raw score, which is 70, subtract the mean score, which is 60, and divide by the standard deviation, which is 10. This time I get 10 divided by 10, which equals 1. This person has a z-score equal to 1. That's because this individual's raw score of 70 is 10 units above the mean, which is equivalent to 1 standard deviation above the mean. So this person's z-score is positive 1, indicating that they are 1 standard deviation higher than the mean. Let's look at the last person. They have a raw score of 55, from which we need to subtract the mean of 60 and then divide by 10. They deviate by -5 units because they're 5 units below the mean. We divide this by 10, and we get that person 3 has a z-score equal to -1/2, or -0.50. When someone has a positive z-score, like person 2, it means that their raw score was greater than the mean. When a person has a negative z-score, however, it means that their raw score was below the mean. And if somebody's raw score is exactly at the mean, their z-score will be 0. So you can always know if a raw score was above or below the mean by whether it was positive or negative. When scores are closer to the mean, they are more common. When scores are further from the mean, they are less common. The reason for this is that if we were to look at the bell curve, we see that it's tallest around the mean. That means scores in this zone are the most plentiful or the most common, and that scores are getting rarer as we move further away from the mean because the graph is getting shorter. As we move further and further into the tails, scores are getting exceedingly rare because the graph is getting shorter and shorter. Therefore, scores at or near the mean are more common than scores that are many standard deviations away from the mean. For example, a z-score of -3 or +3 is really far from the center of the graph. It's down where the graph gets really short in the tails. So z-scores of -3 and +3 are quite rare, whereas z-scores of 1 and -1 are in a fairly tall part of the graph, so they're more common than scores of -3 or 3. So scores closer to a z of 0 are more common or more likely. That means they have a greater probability of existing. Whereas scores further from 0, respectively, are less common or less likely. That means that the higher z-scores, like 3 and -3, have a lower probability of existing or being selected than z-scores of 0, -1, or 1. So z-scores are a way of standardizing scores. Instead of saying that you're a certain number of standard deviations away from the mean, statisticians typically use the term z-score. This describes the exact same thing. When we say a z-score was +1, we're saying that a raw score was 1 standard deviation above the mean. When we say a z-score was -1, we're saying a raw score was 1 standard deviation below the mean. When you compare how far one standard deviation is from the mean compared to another, you are comparing z-scores. If we had a z-score of +2, it would mean our raw score was 2 standard deviations above the mean. Similarly, a z-score of -2 would mean that the raw score was 2 standard deviations below the mean. Remember, when we say a positive z-score, it means we're above the mean, and a negative z-score means we are below the mean. Because the graph is symmetrical, however, a z-score of +2 and a z-score of -2 are equally likely to occur because they are equally far from the mean. One is 2 standard deviations below and one is 2 standard deviations above. So let's take a look at an example. If a distribution has a mean of 100 and a standard deviation of 10, a score of 110 corresponds to a z-score of +1. This is because the z-score formula says take the raw score and subtract from it the mean score, then divide by standard deviation. So if we had a mean of 100 and a standard deviation of 10, and our raw score was 110, we end up with 10 over 10, which is +1. Similarly, if we had a raw score of 80, we would take 80 minus 100, divide by 10, and we get -2. And if we take a raw score of 70, subtract the mean of 100, and divide by a standard deviation of 10, we get that the z-score is -3. We can use the same logic to find the z-score of any number in any distribution. They don't have to just be whole numbers or ones that correspond to whole z-scores. For example, if we had a raw score of 115, we would fill this in the same way. If the raw score was 115, the z-score would be +1.5. If the raw score was 125, the z-score would be 2.5. As noted, z-scores relate back to the normal curve. The z-score is actually telling us the position of a raw score along the x-axis here of a normal curve. A z-score of 0 means a person's raw score is at the mean. If a person's z-score is +1, they correspond to being 1 standard deviation above the mean, where if someone else's z-score was -1, they'd be 1 standard deviation below the mean. But notice here that the height of these two sections is equivalent, so having a z-score of -1 is as likely or probable as having a z-score of +1. And we expect about 1/3 of folks to be from 1 standard deviation below the mean to the mean, and another approximately 1/3 of folks to be from 1 standard deviation above the mean to the mean. So we expect about 2/3 of folks to be from 1 standard deviation below the mean to 1 standard deviation above the mean. More specifically, we expect about 34.13% of folks to be in each of those two corresponding areas, giving us a total in this middle of 68.26%. We'll not go into how those percentages came to be understood at this juncture, but you will want to keep them in mind. We always expect about 68.26% of folks, or about 2/3, to be within 1 standard deviation below the mean to 1 standard deviation above the mean. Z-scores of -2 and +2 are less likely than z-scores of -1, 0, or 1 because they're in shorter parts of the graph. But notice that these two are the same height, so a z-score of -2 and a z-score of +2 are also equally likely to be selected or equally likely to exist. And we expect just over 95% of folks, that's 95.44% of folks, to be from 2 standard deviations below the mean to 2 standard deviations above the mean. Because we see this is a really large portion of our graph, it makes sense that we're saying nearly all scores are here, about 95%. And if we look out to a z-score of -3 up to a z-score of +3, we get 99.72% of scores that are expected to be here. You notice if we color in that graph going from a -3 to a +3, that almost 100% of the graph gets colored in. That corresponds to 99.72% of the scores. Because our graph is symmetrical, about 50% of scores are expected to be from the mean to below the mean, and the rest of the 50% of scores are expected to be from the mean to above the mean. So having any negative z-score has about a 50% chance of occurring, and having any positive z-score has about a 50% chance of occurring. So a negative z-score and a positive z-score are equally likely to occur at about 50% and 50%. Let's practice the concept. If the difference between your raw score and the mean is +20 and the standard deviation is 10, let's find the z-score. What we mean by the difference between the raw score and the mean is x minus x bar. That's called a deviation. So presume in this case that our deviation is +20 and that the standard deviation is 10. In this case, our z-score would be +20 divided by 10, or 2. Pause here and try to fill in the other 4 questions using the z-score formula of z equals raw score minus the mean divided by standard deviation, keeping in mind that the difference between a raw score and the mean is the deviation or top part of the formula, and the standard deviation is the bottom part of the formula. Hit play when you're ready to check your answers. In the second scenario, we have a deviation of 2 and a standard deviation of 2, so the z-score is 1. In the third example, we have a deviation of -2 and a standard deviation of 2, so the z-score is -1 because we're 1 standard deviation below the mean. In the fourth example, the deviation is +1 and the standard deviation is 2, so we're only half a standard deviation above the mean. That means our z-score is 0.5. And in the last example, our deviation is -4, indicating we're below the mean, and the standard deviation is 2, so we are 2 standard deviations below the mean, which gives us a z-score of -2. Pause here and try these 5 questions, then hit play when you're ready to check your answers. In the first scenario, our deviation was 20 and our standard deviation was 5, so the z-score is 4. In the second scenario, our deviation was 12, our standard deviation was 2, so our z-score is 6. In the third scenario, our deviation was -2, our standard deviation was 0.5, so our z-score is -4. In the fourth scenario, our deviation was 7, our standard deviation was 2, so our z-score is 3.5. And in the last example, our deviation was -4, our standard deviation was 1.5, so our z-score is -2 2/3, or -2.66 continuous. Remember, if you were to round 2.66 continuous to the hundredths place, you would get 2.67. It would be incorrect to put that the answer is just 2.66 unless you put the continuous marker on top, or if you write the ellipses at the end indicating that the 6's repeat. So as previously noted, the normal distribution curve depicts quantitative scores only, where the scores themselves appear along the x-axis and correspond to their z-scores. The peak or center of the graph is the mean, median, and mode line. It's the tallest part of the graph that splits the graph into 2 symmetrical halves, the one corresponding to negative z-scores to the left and positive z-scores to the right. Note also that the tails of the graph are theoretically asymptotic, that we could keep drawing this graph further and further out, getting closer and closer to the x-axis without necessarily touching it. Pause here and make sure that you can answer these 3 questions, then hit play. The shape of the curve is bell-shaped. The mean, median, mode are at the center, that's one of the main characteristics. The 2 halves are symmetrical, that's a second characteristic, and the tails are theoretically asymptotic, that's a third key characteristic. raw scores are reported on the x-axis of the curve when the data are normal, and the frequency with which those raw scores occur is reported on the y-axis. Therefore, the height of the curve refers to how frequently scores along the x-axis occurred. Scores are more frequent closer to the mean and less frequent as you move towards the asymptotic tails of the graph. Take a look at this picture of the normal distribution curve that has the center section highlighted, and try answering the following questions. Pause and hit play when you're ready. The proportion of cases expected to fall below the mean is 50% because the center splits the graph in half. That also means that the percentage or proportion of cases expected to fall above the mean is also 50% because the whole graph is 100% and it's split evenly down the middle. The proportion of cases that are expected to fall between 1 and 2 standard deviations below the mean is 13.59%. Correspondingly, the percentage of cases expected to fall from 1 standard deviation above the mean to 2 standard deviations above the mean would also be 13.59%. Now we'll step it up with a slightly harder question. What proportion of cases are expected to fall between a z-score of -1 and a z-score of +2? Well, when I'm trying to find areas between two different parts of the curve, the best thing to do is sketch, shade, then solve. When I sketch and shade, I see that I'm looking for the area from -1 to +2, and though I don't know that total, I can find it by adding. The area from -1 to the mean is identified as 34.13%. The area from the mean to +1 is another 34.13%, and the area from 1 to 2 is 13.59%. So I can add these three areas to get the total percent that falls from -1 to 2. And I find that about 81.85% of scores fall between a score of -1 to +2 if we're using z-scores. Now it's your turn to try it. Sketch a normal distribution curve with a mean of 85 and a standard deviation of 5. Then hit play to compare your graph to mine before answering the questions. I end up with a graph with 85 set at the center, and then I started drawing out the raw scores that corresponded to the z-scores. So I ended up with a raw score of 85 corresponding to a z of 0, a raw score of 90 corresponding to a z of 1, a raw score of 95 corresponding to a z of 2, and a raw score of 100 corresponding to a z of 3. I also had a raw score of 80 corresponding to a z of -1, a raw score of 75 corresponding to a z of -2, and a raw score of 70 relating to a z-score of -3. Notice here that I'm drawing them just from -3 to +3, 3 standard deviations below the mean to 3 standard deviations above the mean. You'll find that's typically true, that we only draw the graph going out from -3 to 3 for z-scores, because that's where about 99.72% of scores are expected to be. Very few scores are expected beyond this because the graph tails have gotten so short, so we typically don't have to continue sketching past a corresponding z-score of -3 and 3. Now pause and try the questions written below. And when you're ready, hit play for some answers. The first question asks you to find 3 raw scores which were common relative to others. There are several numbers that you could have given. The most common is 85, but anything close to 85 would also be considered fairly common, like a score of 80 or 81, 82, 83, 84, 85 we already identified, 86, 87, 88, 89, and 90. Those are all fairly common because they're pretty close to the mean. If we were asking for scores that were rarer, we'd be looking further from the mean. So rare scores would be things like 95, 96, 97, 98, 99, 100, or anything past 100. Even 75, 74, 73, 72, 71, 70, or anything lower than 70. So a raw score of 130 or a raw score of 40 would be really rare because they're way out in the tails. They're not even shown in our sketch because they're in such a narrow part of the curve. Name 3 raw scores which are rarer than 89. Well, we'd first want to identify where that 89 is. It's right around here, and so anything rarer is going to be anything further out into those tails. So a score of 90 or 95 or 100 or 99 or 120. Those are all rarer. But we have another section where things are rarer. Remember that this is symmetrical. So a score of 89 is as common as a score of 81 because they're equally far from the mean. So anything that's below 81, such as 80, 75, 70, 20, 74, those are all rarer than 89 as well. So any number below 81 or above 89 is rarer than 89 because they are further from the mean than the score of 89. If a score was selected at random, how likely is it that it would be between 80 and 90? Let's sketch, shade, and solve. I want from 80 to 90. That's one standard deviation below the mean to one standard deviation above the mean. So I can flip back to my earlier charts and I'll see that this is 34.13% in the lower portion, 34.13% in the upper portion, and if I add those, I get a total of approximately 68.26%, because about 68.26% of scores are expected to be from one standard deviation below the mean to one standard deviation above the mean. If a score was selected at random, how likely is it that it would be between 80 and the mean? Again, sketch, shade, then solve. I have my raw score of 80. I'm looking for the area from there to the mean. We already identified this just a moment ago, but we could look back at our earlier chart, that if we're looking for the area from one standard deviation below the mean to the mean, it's going to be 34.13%. So the likelihood of a score being randomly selected from this area from 80 to 85 is 34.13%. If a score was selected at random, how likely is it that it would be from 90 to the mean? Same idea here. I'm going to sketch, shade, then solve. I'm again looking at an area from one standard deviation above the mean to the mean, so I know that this is going to be 34.13%. So the answer here again is 34.13%. If a score is selected at random, how likely is it that it would be from below the mean? I'm going to sketch, now shade, then solve. When I shade this area, I see that it's half of my graph. So the corresponding area below the mean is 50%. So the chance of grabbing a score from below the mean at random is 50%. Similarly, the chance of grabbing a score at random above the mean is also 50%. Finally, if a score was selected at random, how likely is it that it would be between 90 and 95? I'm going to sketch and shade this area. I can look back at my picture from just a few moments ago in our lecture, and I see that the corresponding percentage here is about 13.59%. The area between these two raw scores corresponds to a z of +1 to +2, and if I look back on the other graph, I see that's 13.59%. That's the same percent that's from a z of -1 to a z of -2. If I had been looking for that area, I would have also found that that is 13.59%. As noted before, the normal curve is just a polygon for a histogram. That means we have that nice bar graph for quantitative data, where we've drawn in those sloping lines, kind of like a connect the dots, and we see this bell-shaped curve emerge. Here I have an example from another data set of percent correct on an exam, where the mean score was 80 and the standard deviation was 10.075. Here we had a sample size of 100. Notice that this graph looks a lot like that bell-shaped curve we saw a moment ago. That's because these data are normally distributed. These are quantitative values that are following that general bell shape. We see the tallest point at the center, sloping symmetrical sides with theoretically asymptotic tails. So our graph here looks fairly normal, even though we're looking at a different data set than the one we were looking at a moment ago. That's because multiple quantitative data sets can be normal. This brings us to the topic of probability. We've already been talking about probability in its relation to the normal curve. That is, we can see how common or uncommon different raw scores or z-scores are using the normal distribution curve. But probability is a bigger topic than just the normal curve. There are lots of different ways that we use probability beyond simply using it in the normal distribution, so we'll review a few of those here. Let's say that something had a 50% likelihood. I could write that as a fraction of 1 over 2. That means the probability is 1/2. In decimal form, I could write the probability as 0.50, or half of 1. And in percent form, I could write it the way I had said it out loud, which is 50%. These three are different ways of writing the same probability, that there's a 50% chance of something occurring. So probabilities can be written in fraction form, decimal form, or percent form. As long as you know how to translate between the three of these, you can use any one in most situations to indicate probability. If an event is certain to happen, then the probability of that event is 100%, or as a fraction it's 1 over 1, and as a decimal it's 1.0. Each of these mean that something is certain to occur. If something is certain to not occur, then the percentage chance that it'll happen is 0%. That's the same as a fraction of 0 over 1, or a decimal of 0.0. When we say the probability of something is 0%, we're saying we are certain it will not happen. If an event is just as likely to happen as to not happen, then the probability is 1 over 2, 0.5, or 50%. So in a nutshell, probability just refers to likelihood. Probability is how likely it is that something is going to happen. Assume I take a regular unbiased coin. If the coin is tossed, there is a 50% chance that it lands on heads and a 50% chance that it lands on tails, because there's only two possible outcomes and they're equally likely to occur. If I roll one standard 6-sided die, the probability of getting a 1 is 1 in 6, because there's 6 possibilities. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. So there are 1, 2, 3, 4, 5, 6 possibilities. The number of possibilities goes on the bottom of the fraction. Of those, one of those possibilities is me rolling a 1. The number of ways something can occur becomes your numerator. So the probability of rolling a 1 on a 6-sided die is 1 out of 6. What about if we want to know the probability of rolling a 4? Well, first we need to figure out how many different outcomes there are that are possible. That becomes our denominator. If I roll a 6-sided die once, my possible outcomes are 1, 2, 3, 4, 5, and 6. That's 1, 2, 3, 4, 5, 6 possible outcomes. And one of those 6 options gives me a 4. So the probability of rolling a 4 is 1 out of 6. The probability of rolling a 1 was 1 out of 6. So if I roll the die once, I have an equal chance of rolling a 1 as I have of rolling a 4. An important thing we need to note is that probability does not tell us what will happen. It simply tells us the likelihood of something happening. Though I have a 1 in 6 chance of rolling a 1, it could happen. It's unlikely that I'm going to roll a 1, because 5 out of 6 of the outcomes do not give me a 1, but it can occur. As long as the probability isn't 0, then what it's telling us is that something has a likelihood of happening. If the probability is 0, it means it has no chance of happening. If the probability is 100%, or 1 over 1 in fraction form, then that means it will happen. Anytime a probability is other than 0 or 100%, it's not telling us what will happen, but simply what is likely to happen. As noted, to find the probability of an event, you need to find the total number of ways something can occur and divide it by the total number of possible outcomes. As noted, if I have a standard 6-sided die, there are 6 possible outcomes. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. So the total number of possible outcomes is 6. Now, if I'm interested in what the probability is that I roll an even number, then I need to identify how many of these constitute an even number. There are 6 possibilities, of which 1, 2, 3 are even numbers. So if I want to know the odds or probability of rolling an even number, it's 3, the number of ways an even number can come up, out of 6, the total number of possibilities. If I reduce this down, I find that the probability, or odds, is 1 out of 2. That means that there's a 50% chance that if I roll the die once, I will get an even number. Let's stick with that die, where there are 6 possible outcomes. Now we need to figure out the ways a specific event can occur. Suppose that I want to know the odds of rolling a number lower than 3. I need to find out how many different ways rolling something lower than 3 can occur. Well, if I roll a 1 or a 2, those are both lower than 3. So there's 2 possible ways that I could roll something lower than 3. I could roll a 1 or a 2. So there are 6 possible outcomes, of which 2 of those ways make the event that the result is less than 3 occur. If I simplify this or reduce, I get the odds are 1 out of 3, or about 33.33%. So to find the probability of something occurring, you must first identify the sample space, that's how many possible outcomes there are, and then identify how many ways whatever it is you're looking for can occur. Then divide the number of ways your event can occur by the number of possible outcomes overall to get the probability. Pause here and try this practice. When you have your answers, hit play. If you flip a coin, the probability of getting heads is 1 out of 2, because there's 2 possible outcomes, heads or tails, of which one of those is heads. So the odds are 1 out of 2. The probability of choosing one of the aces out of a standard deck of 52 cards is 4 out of 52, which we can reduce to 1 over 13. That's because there are 4 aces out of 52 total cards. So your odds are 4 out of 52, or 1 out of 13. The probability of rolling an odd number on a die is 1 over 2. That's because there's 3 odd numbers that you could roll, a 1, a 3, or a 5. And the possibilities are 1, 2, 3, 4, 5, and 6. That means there's 3 ways you can get an odd number out of 6 possible outcomes. So that's 3 over 6, which reduces to 1 over 2. Kelly is the captain of a track team. The team is deciding on a color, and all 8 members wrote their choice on equally sized cards. If Kelly picks one card at random, what is the probability that blue will be picked? Well, first we need to look at how many different possible outcomes there are. There's 1, 2, 3, 4, 5, 6, 7, 8 cards. So there's a 1 out of 8 chance that each of these cards is selected. Now we need to identify how many of them are blue. 1, 2, 3 out of the 8 possible outcomes give us blue. So the odds of selecting the blue card and thus getting blue team jerseys is 3 out of 8, because there's 8 cards that are equally likely to be selected, of which 3 indicate blue. As a bonus, try to figure out what the odds are of selecting red, yellow, or green, each separately. We want to know the odds first of getting yellow, then of getting red, and finally of getting green. Hit play when you want to check your answers. The odds of picking yellow are 2 out of 8, which is the same as 1 out of 4, because 2 of the cards are yellow and there are 8 total cards. So the odds are 2 out of 8. The odds of picking red is also 2 out of 8, or 1 out of 4, because there are 2 cards that indicate red out of 8 total cards. And finally, the odds of picking green is 1 out of 8, because out of the 8 cards, only one of the possibilities is selecting a green card. Therefore, it's the most likely that we're going to get blue, because 3 out of the 8 possibilities gave us blue as the outcome. That's more likely than that we're going to get yellow, which is 2 out of 8, or that we're going to get red, which is also 2 out of 8, or that we're going to get green, which we noted was 1 out of 8. Notice that none of these options are especially likely to occur, because the most likely option is 3 out of 8, which still has a less than 50% chance of happening, because a 50% chance would have been 4 out of 8. So though none of these are especially likely to occur, blue is the most likely to occur because it has the highest odds, 3 out of 8, and green is the least likely to occur because it has the lowest odds, 1 out of 8. Pause here to try this practice and then hit play to check your answers. The probability that the spinner lands on A is 1 out of 4 because there are 4 possibilities, A, B, C, and D, which are all equally likely to occur. And the second one, the probability that the spinner will stop on an even number is 1 out of 3 because there are 3 numbers, 1, 2, and 3, only one of which is an even number. So the odds are 1 out of 3. The odds of an odd number, in comparison, are 2 out of 3 because 2 of the 3 possibilities, the 3 and the 1, are odd numbers. The probability that the spinner in the last problem will stop on A is 1 out of 3 because there's 3 possibilities, A, B, and C, that are equally likely because the slices are equal in size, and only one of them is A. And the last part asks, what is the probability that a spinner with 5 equal or congruent sections numbered 1 through 5 will stop on an even number? We can sketch it to help. I've sketched my spinner with 5 equal parts. Now I want to know the odds of landing on an even number, so I'm going to identify all the evens. The even numbers in here are 2 and 4. So there are 5 possible outcomes, 1, 2, 3, 4, and 5, of which 2, the 2 and the 4, are even. So the odds here are 2 out of 5, which is the same as 0.4 or 40%. Any of those are correct ways of stating this answer, unless otherwise specified. So the odds of getting an even number on this last wheel are 2 out of 5, which is equivalent to 0.4 or 40%. Pause here and try this probability and betting scenario. It helps to sketch the scenario. When you're ready, hit play. If I toss the coin once, the probabilities are 50% that it's heads and 50% that it's tails. If I toss it a second time, on the second toss, it's equally likely that I'm going to land on heads or tails. So in 2 tosses, there are 4 possible outcomes. I could get heads then heads, heads then tails, tails then heads, or tails then tails. So in 2 tosses, we see 4 possible outcomes. Let's take a look at 3 tosses. Each time again, I could get heads or tails, no matter what had happened before. So notice that this is growing exponentially. And now I have 8 possible outcomes that could occur. It could be heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. So there are 8 possible outcomes in 3 tosses. Now let's draw the 4th toss. Each time again, heads or tails could occur, and each time again, I'm doubling the number of possible outcomes because there's 2 possible outcomes every single time. In fact, I've got so many outcomes going on here that I'm running out of space to draw. So if we look at these, I'm going to summarize them in red next to them. The pathway for the first one is heads, 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 all heads. The second pathway is heads, 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 tails, and I'll follow the same pattern all the way down. When I draw them all out, I see that there are 16 possible outcomes. That's the same as 2 to the 4, because it's 2 times 2 times 2 times 2. Only one of those outcomes gives me all heads, and only one of those outcomes gives me all tails. The rest are a mix of heads and tails. So there are 16 possible outcomes. The odds of getting all heads is 1 out of 16, and the odds of getting all tails is also just 1 out of 16. Let's look at a few scenarios here. First, let's find what the odds are of getting all heads. We already noted there's only one way that can occur out of the 16 possible outcomes, so the probability there is 1 out of 16. Now let's find how many different ways we can get just one head in 4 tosses. I see 4 different outcomes that give me 1 heads and 3 tails. So the odds of getting heads just once is 4 out of 16. Now let's look at how many different ways we can land on heads exactly twice. I see 6 out of 16 different ways to land on heads exactly twice. Now let's look at how many ways we can land on heads exactly 3 times. This time I mark them in purple and I see 4 out of 16 possibilities where we get exactly 3 heads. And finally, let's look at how many of these possibilities give us heads 0 times. Well, there's only 1 time that occurs, and that's when we get all tails. So that's 1 out of 16 times. To understand our odds, let's look at these fractions and add them up. We should get 16 out of 16 so that everything is accounted for. So we had 1 out of 16, 4 out of 16, 6 out of 16, another 4 out of 16, and finally a 1 out of 16. When we put all the odds of these 5 different scenarios together, we get a total of 16 sixteenths. So we've got all of the different scenarios accounted for in our odds here. So the outcome that is most likely to occur from these 5 different scenarios is that we land on heads exactly twice. But though this is the most likely, it doesn't mean it's going to happen more than 50% of the time. If it was going to happen 50% of the time, that would be 8 out of 16. But we see it's only expected to happen 6 out of 16 times. So the most likely outcome is to get 2 heads, even though it has a less than 50% chance of occurring. The reason it's still the most likely is because all the other possibilities have a lower likelihood each of occurring compared to getting 2 heads. So let's take a look at our best bet in this scenario. If you had $10 to bet that heads would come up 0 times, 1 time, 2 times, 3 times, or 4 times, if you had to bet, your best bet is to bet on 2 heads. However, your odds are best if you simply don't gamble, because in none of these scenarios is there greater than a 50% chance you're going to win. So no matter what you pick, the odds are you're going to lose your $10. So this is a bit of a trick question. The best thing to do, or the best bet to place in this scenario, is no bet. But if you're going to bet, your best odds are betting on 2 heads exactly. Now let's look at probability rolling 2 6-sided die. The first die could land on 1, 2, 3, 4, 5, or 6. And the second die could also land on 1, 2, 3, 4, 5, or 6. So there are 36 possible combinations that can happen here. I can roll a 1, then a 1, a 1, then a 2, a 1, then a 3, a 1, then a 4, a 1, then a 5, a 1, then a 6. That's 6 different outcomes. Or a 2, then a 1, a 2, then a 2, a 2, then a 3, a 2, then a 4, a 2, then a 5, a 2, then a 6. That's 6 more possible outcomes. So on and so forth. End up with a total of 36 possible outcomes. We can do this in exponent form, where the number of possible outcomes each time is the base, and the number of times we invoke it or roll the die becomes the exponent. So there are 6 possible outcomes squared because there's 6 outcomes twice. So that's 6 that could occur times 6 other things that can occur. And you'll see we get 36 unique outcomes. Now you may notice that some of these appear redundant, like we have a 1 then a 2 and a 2 then a 1. But these are actually 2 different things that can occur. I can roll a 1 then a 2 or a 2 then a 1. These are 2 different scenarios. So there's twice as much chance of rolling a 1 and a 2 in either order as rolling a 1 and a 1. Because there's only one way to roll a 1 twice. The first die is a 1 and the second die is a 1. But there's 2 ways to roll a 2 and a 1. I could roll a 1 then a 2 or a 2 then a 1. So let's look at our total possible score in 2 rolls. Your total possible score is how many points you earn in 2 rolls of the die. To find that, I'm simply going to add each of the 36 unique scenarios. Each of these scenarios are equally likely to occur. There's a 1 in 36 chance of getting a 1 then a 1, a 1 in 36 chance of getting a 1 then a 2, a 1 in 36 chance of getting a 2 then a 1. But there's a 2 out of 36 chance of getting a 1 and a 2 in any order. So when I add the total for the 2 rolls, I find that the lowest possibility is rolling a total of 2, and the greatest possibility is rolling a total of 12. But there are several different ways that I could roll a 7, And there are a few different ways that I could roll 6s or 5s. So there are multiple different combinations that are yielding most scores, with the exception of yielding a 2 and a 12, for which I only see one possible combination. So let's organize this into a table. Here I have all the possible outcomes, and here I have the totals from the previous slide. Let's take a look at how many different combinations give me a total of 2. I'm going to look at the information down here to find the totals. I see that there's only one way to get a 2, and I see there are 2 ways to get a 3. Pause here and fill in the rest of the table to find how many different combinations yield each of the totals. You should get that there's one way to get a 2, 2 ways to get a 3, 3 ways to get a 4, 4 ways to get a 5, 5 ways to get a 6, 6 ways to get a 7, 5 ways to get an 8, 4 to get a 9, 3 to get a 10, 2 to get 11, and only one way to get a 12. If you were to add all those combinations, you'd find that the total is 36, because there's 36 possible outcomes that are divided into these different totals. The combination that has the greatest probability of happening is getting a total of 7. There are 6 different combos that give you a total 7, but take a look at your odds there. Your odds of rolling a total 7 is only 6 out of 36, or 1 out of 6. The odds there are the best of any of the totals, but they're still pretty bad, because there's a 5 out of 6 chance that you are not going to roll a 7, even though the combination of rolling a total 7 is the most likely. So let's plot the frequency with which each of those combinations from 1 to 12 can occur. There was one way to get a 2 and 2 ways to get a 3. So I'm going to draw those bars at a height of 1 and 2 respectively. Sketch on your own and fill in the rest of the graph. What you should end up with is a graph that looks a bit like this. Notice that we've got the tallest part at the center with these kind of sloping, fairly symmetrical descending sides. Our data here look fairly normal. So here we plotted the likelihood or the probabilities of different outcomes of the die. That is, how many different ways that each of the totals can be rolled. And here we saw that the most commonly rolled combination is going to result in a total of 7. And the least likely rolls are going to result in 2s or 12s, because that's the shortest part of our histogram, or our bell-shaped curve here. Pause and try this practice, then hit play to check your answers. Assume there are 5 numbered pieces of paper in a bag which are all of equal size and shape. They are labeled 1, 2, 3, 4, and 5. If these are all in the bag together, then if I reach in and randomly grab one, they are equally likely to occur. So what is the likelihood that if I pick one of the pieces of paper out of the bag at random, that it is a 2? Well, there's 5 possibilities, of which one of them gives me a 2. So the likelihood is 1 to 5, 1 out of 5. The second scenario asks, what is the likelihood that if you pick one out of the bag at random, that it's a 5? This again has 5 possible outcomes, only one of which gives you the 5, so the ratio in part to whole is 1 to 5. And finally, what's the likelihood that if you pick one of the slips out of the bag at random, that it's a 2 or a 5? Well, there's 5 possible outcomes, 1, 2, 3, 4, 5, of which 2 of them give me 2 or 5. So the odds here are 2 out of 5, or a part to whole ratio of 2 to 5. So let's take a moment to step back and understand why it is we're talking about probability in a video that's about pre-statistics. Statisticians work with probabilities, not certainties. Particularly statisticians in the behavioral and social sciences, where we don't get guarantees. We're never 100% sure of anything. At times we might be 95% sure that our results are reflecting reality, but that means there's a 5% chance that our results do not reflect reality accurately. You might hear the word significant used in statistics. When a statistician says a result is significant, what they're saying is there's less than a 5% chance that this is a randomly occurring event. That means they're 95% sure that what they're seeing reflects reality and isn't just due to the 5% chance of something weird happening in their data, if data are collected well. So notice here that when a researcher in the behavioral sciences says the result is significant, they're not saying they're 100% sure their result is accurate. They're saying they're 95% sure that their result is reflecting reality. That means there's a 5% chance that their result is an inaccurate reflection of reality. We're willing to take a 5% chance or risk of having this kind of wrong answer because the evidence is heavily in our favor when we say we're 95% sure. So for these reasons, it's really important that we start to understand how probabilities work in scenarios like rolls of the dice and flips of the coin, because understanding probability is an important precursor to understanding college-level statistics like you might learn in a Statistics 101 course.